Hey guys, today we're going to learn about particle motion. Now, particle motion problems are dealing with particles that are moving either along the x-axis or the y-axis. So what that means is essentially the particle is moving either strictly horizontal or vertical. Our position, velocity, and acceleration functions that we're going to look at today are functions, and so their graphs may look curvy or they may look like polynomials or lines, but that does not mean that the particle moves along the graph of the function. The graphs are just going to describe how it's moving side to side or up and down. So let's have a look at average velocity. We have here average velocity is equal to P of A minus P of B over A minus B, which essentially what this is the slope of the secant line of the position function. So we get average velocity from 2 points of position. Now, as a side note, position function, I'm using P of T, P for position, but it could also be named as S of T or X of T or basically any other function. Now, instantaneous velocity is when you get the derivative of the position function. So remember that we learned the difference between average and instantaneous rates of change. If it's average, that's the slope of the secant line, as we just discussed. And if it's instantaneous, it is the derivative. And we're given a value that we would plug in. So let's have a look at an example and how we would find the average velocity and then the instantaneous velocity. A particle's position is given by the function P of t is equal to 3t squared minus 4t plus 1, where P of t is measured in centimeters and t is measured in seconds. What is the average velocity on the interval 1 to 3? So if I want my average velocity, whoa, that's big. If I want the average velocity, I am going to do my secant line, again, because of that keyword here, average, and you're given 2 points here. So this is going to be P of 1 minus P of 3 over 1 minus 3. We need here the value of P of 1, and then we're going to need the value of P of 3. So for P of 1, I'm going to plug that in. So that's 3 times 1 squared, which is 3, minus 4 plus 1. 3 minus 4 is negative 1, plus 1, 0. Now I'm going to plug in the 3. 3 squared is 9, times 3 is 27, minus 4 times 3, which is 12, plus 1. 27 minus 12 is 15, plus 1 is 16. So I can plug in these values now for P of 1 and P of 3. So P of 1, 0, minus P of 3, which is 16, over 1 minus 3, which is negative 2. This gives me negative 16 over negative 2, which is 8. And our units here, if we're given that position, is centimeters, and then I'm dividing by 1 minus 3, which is the time, that's going to be centimeters per second. Now, for the next question, what is the instantaneous velocity of the particle at 1.5 seconds, and what does this value represent? So let's start with finding the derivative of position, which the derivative of position is the equation for velocity. So I like to always write this down so I know what it is exactly that I'm looking at. The derivative here would be 6t minus 4. So now when I plug in 1.5, so v of 1.5, or you can write p prime of 1.5, both are the same, is going to be 6 times 1.5 minus 4. 6 times 1.5 is 9. And 9 minus 4 is 5. And again, this represents my velocity. And my units for velocity are centimeters per second. So what this value represents is that the velocity of the particle at t equals 1.5 seconds. So the derivative of position is the velocity of the particle, more specifically the instantaneous velocity. Now let's have a look at acceleration. So as you notice, average velocity is the slope of the secant line to the position function, and instantaneous velocity is the slope of the tangent line to the position function. And it goes to show that it's the same thing for acceleration. Average acceleration is going to be where you find the slope of the secant line of the velocity function. And instantaneous acceleration is the derivative of velocity, or the second derivative of the position function. So here we have the same scenario as the previous one, where p of t is 3t squared minus 4t plus 1. If I want to know my average acceleration, this is going to be v of 1 minus v of 3 over 1 minus 3. In order to get v of 1 and v of 3, I need the equation for velocity. We can get velocity by finding the derivative of p of t, which we did earlier. That was the 6t minus 4. Now I can plug in the 1 and the 3. So v of 1 is going to be 6 times 1, which is 6, minus 4, so 2. And then when I plug in 3, 6 times 3 is 18, minus 4 is 14. When I plug them in, v of 1 is 2 minus 14 over 1 minus 3, which is negative 2. 2 minus 14 is negative 12. Divided by negative 2 gives me 6. Now for my units, velocity is in centimeters per second. And then if I divide by seconds, that gives me centimeters per seconds squared. So something to take note. Velocity is always your unit of measurement over time, whereas acceleration is your unit of measurement over time squared. So if you ever get confused on what your units may be, velocity is not squared, where acceleration is squared for time. Now, for the last one here, what is the instantaneous acceleration of the particle at 1.5 seconds, and what does this value represent? So instantaneous acceleration, is from the derivative of velocity. So a of t, which is a for acceleration, is equal to v prime of t. Now v prime is 6. So that means that a of 1.5, there's nothing to plug in. It's going to be 6. And our units would be centimeters per second squared. So what this value represents is this is the acceleration of the particle at t equals 1.5 seconds. Acceleration also means that if it's positive, that means that the velocity, which is the previous function, is increasing, since it is the derivative of velocity. If acceleration is negative, then that would mean that the velocity is decreasing. So basically, let's break this down. Our initial function, this corresponds with the position of the particle. Our first derivative corresponds with the velocity of the particle, and the second derivative corresponds to the acceleration of the particle. So all of the relationships that we learned in the past with f, f prime, and f double prime applies here as well. It's just now, instead of using f prime and f double prime, we are using velocity and acceleration. So these are what I call the 6 commandments of particle motion, so something to keep in mind. Velocity gives the direction of the particle. Remember that our particles are either only moving left and right or up and down, but most of the time it's horizontal. If the velocity is positive, this means that the particle is moving to the right. Or if we are told that the particle is moving along a vertical axis, then it would mean that the particle is moving up. If the velocity is negative, then that means that the particle is moving to the left. And again, if it was on a vertical axis, that means that it's going down. Speed is not the same as velocity. Okay, velocity associates the speed, but it gives direction. Speed does not give direction, so therefore it is the absolute value of velocity. Speed is how fast the object is moving, no matter which direction it's going. Now, to figure out whether the speed is increasing or decreasing. If the speed is increasing, then that means that velocity and acceleration are the same sign. So if velocity is positive and acceleration is positive, that means that the particle is moving to the right at a faster rate. If the velocity is negative and acceleration is positive, then that means that the particle is moving to the left, but at a decreasing speed. So just keep in mind, same signs mean that whether they're both positive or both negative means that the speed is increasing. The speed is going to be decreasing if velocity and acceleration are opposite signs. So if you have your negative velocity and a positive acceleration, that means that it's moving to the left, but it's trying to go back down, so it will be slowing down. So same signs, speed is increasing, opposite signs, speed is decreasing. And finally, if the velocity is 0, but the acceleration is not, then that means that the particle is stopped moving, but is changing direction. So it's kind of like at a standstill, it's standing still at a certain spot, but it's still turning around. That's why the acceleration is not negative, or is not 0. So now let's put this together on a graph. At which point is the velocity equal to 0? Now this graph here, we are told, is the position function. So I'm just going to label this P of t. So remember that position we associate with f of x, our original function. At which point is the velocity equal to 0? Remember that velocity is the first derivative. And we know that our first derivative is equal to 0 when we have extrema, because those would be our critical numbers. So here it would be at b and d. And the reason would be because P of t has extrema. At which point is the acceleration equal to 0? So acceleration, this is the second derivative. And if our second derivative equals to 0, then that means that we have a point of inflection. So by looking here, I can see that this is concave down, and then it's concave up. It switches concavity here at C. So this is at C, and we would say because P of t has a point of inflection. On which interval is the particle's velocity positive? The velocity will be positive. Again, this is the first derivative, and our first derivative is positive when the original function is increasing. So we would look here for where this is increasing, which would starts increasing, so that's from negative infinity until point B, and then again from D and forever to the right, which is infinity. And our reason here would be because P of t is increasing. All of this should start sounding familiar from when we were reviewing our relationships between our functions, the first derivative and the second derivative. On what interval is the particle's velocity negative? So if it's If the particle's velocity is positive when my function is increasing, then that means that my velocity will be negative when my function is decreasing, which occurs from B to D. And our reason here would be because P of t is decreasing. On what intervals is the particle's acceleration positive? Again, acceleration is the second derivative. And the second derivative is positive when my function is concave up. So here our concavity, where it's positive, would be from c and the rest of the time. So that would be from c to infinity. And our reason would be because P of t is concave up. On what interval is the particle's acceleration negative? This is when our function will be concave down. So that would be from negative infinity until c, and again, like I just said, because P of t is concave down. So once again, this is the same thing we've done before, except instead of using f, f prime, and f double prime, we are using P of t, V of t for the first derivative, and A of t for the second derivative. Let's have a look at a word problem. Suppose the velocity of a particle is given by the function v of t is equal to t plus 2 times t plus 4 squared, where t is greater than or equal to 0, where t is measured in minutes and v of t is measured in inches per minute. Find the values of v of 3 and v prime of 3. Based on these values, describe the speed of the particle at t equals 3. So first, let's start with v of 3. I'm going to plug in 3 into my function. So this is 3 plus 2, which is 5, times 3 plus 4, which is 7, squared. So this gives me 5 times 49. And 5 times 49 is 245. Since this is v of 3, this is velocity, which is in inches per minute. Now we need v prime of 3, but before I can find v prime of 3, I need v prime of t. And remember that v prime of t, that is my acceleration function. So I'm going to take the derivative. You can do so in two ways. You can either multiply everything out and then use the power rule, because it will be a polynomial, or you can use the product and chain rule. I know sometimes we don't like to use that method, but I'm going to show you why here, if I use the product and chain rule, how at the end it will be a bit of an easier way. So I'm going to use the product rule and then the chain rule when it comes to this part. So the derivative of t plus 2 will be 1, and now we leave the t plus 4 squared, plus, now I leave the t plus 2, and I multiply with the derivative of this, meaning the chain rule, so I'm going to bring the 2 to the front, times t plus 4. And then the derivative of the inside, which is just 1. In the end, all I care here is v prime of 3. I don't need an equation, like the question wasn't asking what is the equation for A of t. So I don't need to simplify this if I don't want to. I'm going to go ahead and just plug in the 3. So v prime of 3, which is my acceleration when the t is equal to 3, is going to be 3 plus 4, so 7 squared, plus 3 plus 2, which is 5, times 2, times 3 plus 4, which is 7. This is going to give me 49, plus 5 times 10, 5 times 2 is 10, times 7 is 70. So in total, this is 119, and then our units for acceleration would be the inches per minute squared. Since remember, acceleration, time is always squared. So now where it says here to describe the speed, what that means is speed increasing or decreasing. So what you have to do is compare the signs of v of 3 and a of 3. Since they are both positive, this means that the speed is increasing at t is equal to 3, and we would of course write out the reason why, which would be because v of 3 and a of 3 are the same sign. If you had gotten that one was positive and one was negative, then that would mean that the speed is decreasing because they're opposite signs. And this is just an additional note. If I had gotten that this was negative and this was negative, the speed will still be increasing because they would be the same sign. That just means that it's moving to the left at a faster rate. For part B, on what interval is the particle moving to the left, to the right? Show your analysis and justify your answer. Direction, this comes from the velocity function. So just like how we create our number line for our derivatives to get when the function is increasing and decreasing, we do the same thing here. We do our number line using the critical numbers of velocity. When it's positive, the particle is moving right, and when it's negative, the particle is moving left. Since this is already my velocity function, I don't need to take any derivatives. I am going to use this equation to get my critical numbers, which based on that equation, my critical numbers are t is equal to -2 and -4. Now here's the thing, t stands for time, and we cannot have any negative time. So these critical numbers do not matter. And again, it says so here for t is greater than or equal to 0. These are less than 0. So I still need to create my number line though to figure out what direction the particle is moving. So I'm going to do v of t, but instead of having my critical numbers, time starts at 0. So I'm going to plug a number to the right of 0. Let's say 1. 1 plus 2 is 3. And then 1 plus 4 is 5, both of which are positive, so this is all positive. My function here does not change signs after that, since the only critical numbers I got were these two. So this means that the particle is always moving to the right. And the reason would be because v of t is greater than 0 and never less than 0. All right, we're nearing the end. Let's look at a graph. The graph below represents the velocity measured in meters per second of a particle moving along the x-axis. So this is the velocity function. For this first part, at what values of t does the particle have no acceleration over the interval 0 to 10? Because this only goes through 10. Justify your answer. Now, no acceleration does not mean that the acceleration is equal to 0. It means that since acceleration is the derivative of v of t, if there is no acceleration, that means that it is undifferentiable at a particular value. And we know that our functions are not differentiable at cusps, which would be here, 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 and here. Those are all cusps. And I'm not including my endpoints because it's over the interval 0 to 10, where 0 and 10 are not included. So there would be no acceleration at t is equal to 1, 3, 6, and 8. And the reason would be because v of t has cusps and is not differentiable. For what values of t is the particle moving to the right and to the left? So if it's moving to the right, that means that v of t is greater than 0, meaning it would be above the x-axis. And if it's moving to the left, then velocity would be negative, so below the x-axis. So let's start with moving to the right. Those intervals would be from 0 to 2, and then again from 7 to 10. And this is because v of t is greater than 0. Now it's moving to the left when it's below the x-axis, which is from 2 to 7. And the reason would be because v of t is less than 0. For part C, express the acceleration a of t as a piecewise defined function on the interval 0 to 10. Now remember that a of t is the derivative of v of t. So if I want to write this as a piecewise function, we have for this piece here, this is a line, and the derivative of this line is the slope of the line, which the slope, it goes up 3, right 1, would be 3. And that is for the interval, this is from t is equal to 0 to t is equal to 1. So we would put 0 is less than t is less than 1. Now we go to the second piece. We have this other line. The derivative of this line is again the slope. So I'd have to go down 3, right 1, or you can do down 6, right 2, which would still give you negative 3. And the interval would be from t is equal to 1 to t is equal to 3. For this next section, we see here that this is 0. There's no rise, so that's 0, over the run, which is 3, but 0 divided by anything is 0. And that is from the time t is equal to 3 until t is equal to 6. Now notice that I'm using all less than symbols, and this is just letting you know that t is greater than 0 but less than 1, so that's this section. It's just that t is in between. And then I don't put the line underneath because remember that these are undifferentiable, so I cannot include those points. Moving on to this next section, we have yet another line, and the slope of that line is 3 over 1, so 3. And that is from my interval from t is equal to 6 to t is equal to 8. And our last section here is one more line. Again, the slope is down 3, right 2, so that's negative 3 over 2. And this is for where t is 8 until 10. And this is basically my acceleration written as a piecewise function. What I've done is I found the derivative of every section of my graph of v of t by finding the slopes. Last part here, find the average acceleration of the particle on the interval 1 to 8 and show your work and indicate units of measure. So average acceleration, since I'm given an interval, this is going to be v of 1 minus v of 8 over 1 minus 8. This is the graph of v of t, so v of 1 is 3 minus v of 8, which is 3, over 1 minus 8, which is negative 7. In the numerator, we get 0 over negative 7, and 0 divided by anything is still 0. So my average acceleration is 0, and then my units here, since velocity is meters per second, then that means that acceleration is meters per second squared. And that's particle motion.